Welcome back, all of you. Now, since last 2 or 3 classes, we started discussing about some of the practical considerations that we need to look into while recording the NMR spectrum. We discussed a lot about how to choose the spectral width, how to choose the offset, what is single channel detection, what is quadrature detection, how do you tune the magnetic field, how do you shim the magnetic field, what type of sample you require, how do you choose the spectral width, how do you calibrate 90-degree pulse, all those things we discussed in depth. Now let us assume you have understood everything and you are now in a position to record the spectrum. You have collected the time domain data and now you are in a position to do the Fourier transformation and start processing the data. Of course, I already showed the spectra and I said you can do the Fourier transformation and you got the spectrum. But little bit deeper we can go now and see how we can process the data. This is our focus on NMR data processing. There are certain practical considerations in getting the spectrum while processing the data. Of course, we should know we have to do the Fourier transformation. And after getting the spectrum, sometimes we use window functions. What are these window functions? Why are they used? We will discuss. And we can manipulate time domain data either to achieve sensitivity or the resolution or both. We can manipulate this. So these are some of the points we need to discuss. Let us start with Fourier transformation. Of course, we have been discussing even from the early classes, first, second, or third class itself. We were discussing time domain signal can be converted to frequency domain by a mathematical operation called Fourier transformation. Then I said time and frequency are Fourier pairs. So this is this formula for converting the time domain into frequency domain. You collect the signal as a function of time and do this mathematics, and then you will get all the frequencies present in that. Of course, you can do the reverse also. If I have a frequency domain signal, I can do inverse Fourier transform and get the time domain signal. These are interchangeable. These are called Fourier pairs. Exactly what we do in NMR is same. As I have been telling you, in NMR, we collect the signal in time domain, which I refer to as free induction decay. We apply a radio frequency pulse, and then in the absence of the pulse, magnetization starts precessing freely. When it starts it while precessing, it induces EMF in the receiver coil which we collect, and it is a damped oscillation. The signals start decaying, which we said is free induction decay. And we collect this as a function of time, which we saw even in the last class and several other classes. And we do the Fourier transformation. Now we are going to get a frequency domain spectrum. This is what it is all about NMR. You collected the signal in the time domain like this. What happens in the time domain is the signal intensity varies with time as a function. It's a damped oscillation. Now the Fourier transformation of this gives you peaks with varied intensities. This may have an intensity like this, other may have intensity like this, other may have a small intensity. Does not matter. Finally, what happens in the time domain is the variation of the intensity of the signal as a function of time. Here is the variation of the intensity of the peaks in the frequency domain. Okay, that's what all about. So basically, you don't know anything. All you do is simply collect the signal and give a simple command called Fourier transformation in the instrument, and computer is going to give you the spectrum like this. This is what you finally require to do the analysis. Now let us see what happens to the magnetization. We'll discuss little bit about components of the magnetization. Now, if the magnetization M naught is brought to the transverse plane by applying a 90-degree pulse, which we already knew how to calculate 90-degree pulse. I am applying a 90-degree pulse, brought the magnetization to XY plane. Let us say I am going to bring it in this X axis. Now, we have X and Y components of this. Remember, this magnetization is a vector. We can resolve into two components. Look at this one here. The precision, how it is undergoing precision. The magnetization is here, starts going like this, start going like this, start going like this. So you can resolve them into two components, mx component and my component. That is cosine and sine component. We also discussed this in the previous class. We call it as real and imaginary. And after Fourier transformation, I said it is an absorptive and dispersive type peaks. Okay. So the detected signal here in the time domain signal, we can resolve them into two components, cosine and sine, real and imaginary components. This we can represent by a simple equation like this. This we already knew earlier also. An oscillating wave with an amplitude and a frequency is always represented like this. Now, mx component of this I represent as m naught into cosine of omega t. What is m naught? M naught is our magnetization, which is in thermal equilibrium m naught. When the magnetization is initially before application of the pulse, the magnetization which was along z axis. That is considered as m naught. Now this m naught has two components. Ms correspond to cosine component, which is written as m naught into cosine of omega t, where omega is the frequency. My is equal to m naught into sine of omega t. This is simple. I think you all know we can resolve this magnetization into two components. Now, the signal that is detected in the time domain is proportional to this magnetization. What is the amount of magnetization present in the x-axis or in the y-axis or the component of the magnetization? That is what the signal is going to detect. This we saw earlier also. Let us say the Sx is the signal in the magnet in the x-axis. I call it as S naught cos omega t. Mx m naught was the total magnetization. Now I am taking signal in the time domain Sx of t corresponds to S naught into cos of omega t. The same y component signal in the y-axis as a function of time is S naught into sine of omega t. Okay, but the total signal St is the sum of Sxt plus Syt, like M0 is equal to Mxt plus Myt. Earlier in the previous slide we saw. Now in what I am telling is when the signal which we are collecting in the time domain S of t can be resolved into two components, signal along x-axis, signal along y-axis, collected as a function of time. So total signal is sum of Sx of t plus Sy of t. This is the total signal that we are collecting. This is FID. Now we know what is Sx. Sx is equal to S naught cos of omega t and Sy is equal to S naught sine of omega t. Plug in these numbers, plug in these terms here. So total signal is written as S of t is equal to this thing. Now, you can express this as an exponential. This is a basic trigonometry you would have studied in the early days. So now combining these two, we can write as S of t is equal to S naught into exponential I omega t. Okay. So the transverse magnetization decays with the time constant T2. It is a signal which we are collecting. But how does it, how are we collecting it? It is also decaying, you know that. I said there is a decay constant, it is a damped oscillation. And we already discussed earlier the decay of the magnetization in the transverse plane is called T2, spin relaxation time. We already discussed this. It is a relaxation time in the transverse plane. That is the total defacing time in the XY plane, in the transverse plane. So this has to happen. It is a decaying function. So plug it in. So since it is a decaying signal, of course, when you do the Fourier transformation, you are going to get a Lorentzian. That is the first part. Now, when you do the Fourier transformation, you get absorptive Lorentzian and imaginary part called dispersive Lorentzian. Okay, that is apart from that. Now, first you plug in decaying component. This is an exponential function. This we knew. We are collecting the signal. You plug in exponential of minus t by t2. This we are plugging in because we know signal is decaying as a function of t2. Now, what is this going to tell us? What happens if t2 is shorter? Signal decays very rapidly. Okay? Signal decays very rapidly. If the T2 is longer the T2, signal takes more time to decay. That is the physical explanation here. Look at this term. So this decay term depends upon T2. So you can talk about the decay of the signal in terms of T2. Okay. Before we proceed further, since we are doing Fourier transformation, I want to tell you few functions. You just remember, you can work out because we knew the equation for Fourier transformation. I told you, no. So I have given you already the equation for the Fourier transformation. You can use that, like f of t, f of omega is equal to integral of minus infinity to plus infinity, f of t e to the power of I omega t dt. That's we wrote already. I showed you in 2-3 slides before. You know, you can plug all these functions what you want. What is the time domain function? If you know their conditions, boundary conditions of the function, how you can work out and find out the Fourier transform. You can do the Fourier transformation of all the functions. Let us say I have a single sine or a cosine function. Of course, this is a cosine function, and this is a sine function starting from the origin. If I do the Fourier transformation of these functions individually, you get a delta function. Where does it come? At the oscillation, you can calculate the frequency from the separation. This is lambda. You know that. Inverse of that is the frequency. So you can find out the oscillation frequency, okay, and it is a delta function. I'm just giving you the information. Please remember, because we will be using Lorentzian, Gaussian, etc. after the Fourier transformation. On the other hand, let us say I take an exponential decay function. If it is exponential decay, like we saw in the previous slide, our signal it is decaying exponentially. If you do the Fourier transformation, you must get the Lorentzian. This is the important thing. And this Lorentzian function is an FID, is a spectrum like this you get. Okay. Now you can calculate the full width at half maxima. This one. This is given by 1 over omega. If it is exponential omega t, this full width at half maxima is given by 1 over omega. This is a exponential function. NMR signal, what we detect in the solution state, is an exponentially decaying function. So the frequency domain spectrum is a Lorentzian. Of course, you should know this. We come across very often. We already discussed in the previous class while discussing something about FID truncation. Okay. So this is like a square pulse or a rectangular pulse. You take it. Depending upon the width of this, if you do the Fourier transformation, of course, you get a sinc function. This is called a sinc function. And the zero crossings here is inversely proportional to this width. If this width is t, the zero crossings is equal to here minus 1 over t, here plus 1 over t. See, this is the Fourier transformation of a rectangular function. Conventional 90-degree pulse, what we use in NMR, is a rectangular pulse, depending on the width, or you can call it a square pulse. But the frequency spectrum is a sinc function. Please remember, these are some of the things which you can work out. If by mathematics, I don't want to work out each and every function, do the Fourier transformation and show you what it is. But I'm just giving you what is the starting function in time domain, what you get in the frequency domain. If I take a Gaussian, let us say Gaussian function, and do the Fourier transformation, interestingly, you get in the frequency domain also a Gaussian function. We come across this very often when we do the selective pulses, where only a single spin is selectively excited. In an ensemble of molecules, I can selectively excite a particular spin, a band of frequencies. Then I tell you, we come across such things. That's why I'm giving you this information. It is a Gaussian function. If I say the Fourier transformation of that is also Gaussian. We also come across what is called a periodic delta function. What is delta function? It has no width and it has infinite intensity at particular frequency 0, and its value is 0 on anywhere at any point outside the 0. It's a delta function. And many such periodic delta function is called a Coombe function. And this Coombe function, how often it repeats, is given by t. And interestingly, the Fourier transform of this is also a Coombe function with period 1 over t. This is what the reason for high frequency peaks appearing at the low frequency end of the spectrum and vice versa if you do not obey Nyquist theorem. You understand? Remember what is the periodic function? It is a Coombe function and it transforms into a Coombe function with period is equal to 1 over t. Okay, with that we will come back to our expression. Signal t we detect in the xy plane is like this, both x and y axis combined together, expressed as an exponential function, and we have incorporated the decay function because of T2 damping oscillation. Now Fourier transformation of this signal gives the frequency spectrum with cosine part is pure absorptive and sine part is pure dispersive. Look at it. This is called absorptive spectrum. This is called dispersive spectrum. And at the center of this, you are going to get frequency of the oscillation. And at the center of this here, at the zero crossing point, you get the frequency from the dispersive spectrum. Simply remember the decaying function which you collect in NMR. When you do the Fourier transformation, you get two types of peaks. This is called a real part. This is called imaginary part. It is called absorptive signal. It is a dispersive signal. Okay. Now, I said this has a function exponential e to the power of exponential minus t by t2. Okay. Now, I also said in the Lorentzian, it depends upon full width at half maximum is equal to 1 over omega, I said. Remember in one of the slides when I said e to the power of minus I omega t, somewhere here I said, here. Okay, then the transverse magnetization decays with a kind time constant T2, not here, somewhere I said, okay. It's here. It is full width at half maxima is written by inverse of that frequency. So now we are seeing here e to the power of minus t by 2. So we can get the inverse of that line width. If I know what is this line width, I know what is the decay constant. This T2 I can get it. The full width at half maxima of this absorptive signal is given by 1 over pi T2. So if I know this, I know approximately or more precisely what is T2. What does it mean? I can approximately calculate the spin relaxation time. Okay, if I have a broader signal, what does it mean? If I have a broader signal is decaying very fast. If I have a sharper signal like this, if the full width at half maxima is very small, we get sharp signal. That means the signal will be decaying for a long time. Look at here, the FID is dying down very fast. As a consequence, if you collect for a short time and do the Fourier transformation, you have a larger line width. So, the width of the spectrum, full width at half maximum, inverse of that will give you T2. That is spin relaxation time. Remember, if you do not understand anything, at least please remember, faster the signal decays in the time domain, broader the signal in the frequency domain. It decays very fast here, it gives a broad signal. If it decays very slow here, it gives a sharp signal. So, I told you in one or two classes while doing the shimming, you have to ensure that signal decays very fast. You get a log signal, you have to use the log signal to tune the homogeneity. When you are shimming the shim coils, finally you get a better homogeneity. Essentially, you will see that the free induction decay will be decaying for a longer time. Longer the time it decays, sharper is the signal in the frequency domain. But remember, whatever may be that, signal may be broad or sharp. Don't get confused. Nothing is happening. The area of the peak remains same. Area will not change. Whatever happens, the area remains same. So you can still integrate the signal and know how many protons are present in each peak. Remember, while analysis, I will discuss this. The area of the peaks will tell us the number of protons present in that peak. You can compare relatively with some other peak. If I know the peak which has only one proton, depending upon that, relative to that, you find out the area of the other peak, you find out how many protons are present. Remember, I gave the example of proton count with integral intensity with a couple of examples earlier. So that means you can still continue to do the integration irrespective of the fact whether the peak is sharp or broad, area remains same. It will not change. And still you can find out the number of protons present in each of these peaks. Let us now start questioning bit more. Let us start questioning bit more. So far I took only one signal, one decaying frequency to understand different components of this, etc. In the reality, in the NMR spectrum, it is not there, only one signal is not there. The FID does not contain a single frequency. There are so many peaks in the spectrum. There will be a lot of frequencies, many frequencies will be there. Then the question is, what happens if you have many frequencies in the spectrum? How does it work? Write down, let us say we have 3 frequencies in time domain. We've worked out this example. Signal S0 as a function of, ST as a function of T2, it is decaying. We wrote this expression. Now let us say this is for frequency 1. I have another time domain signal with the frequency omega 2. One more peak is there and one more peak is there. Let us say 3 different types of time domain signal, each of them with a different frequency and having different T2. They are decaying. If I have a single frequency, you saw a single oscillatory signal. And all the 3 are there. It could be many more. Then you are going to see in the time domain signal an interferogram. Now question is, if there are many such FIDs, many such time domain signals, the FID is the contributions from each of the signals. FID is the contributions from each of the signals. Also, one of the important points to remember is Fourier transformation is a linear process and the frequency spectrum is the sum of Fourier transform of individual time domain functions. There are 3 FIDs in the time domain corresponding to 3 frequencies which were present. Do the Fourier transformation, you will get 3 frequencies. Now, in a realistic NMR spectrum, there will be n frequencies present. You have n decaying signals, each with a different T2. No problems. Each of them, we have a different T2. They are all decaying signals. Collect them. It is an interferogram, you do not know. It is a mixture. Do the Fourier transformation, you will get individual frequencies, n individual frequencies. So from the, it doesn't matter. The explanation which was given for a single FID holds good if the time domain signal has a superposition of several frequencies. Finally, do the Fourier transformation. That being a linear process, you are going to get frequency domain spectrum with as many number of frequencies which is present in the time domain signal. Okay. Now, we have to do what is called phase correction in the frequency domain. We discussed about pulse phases and phases of the signal. In the previous class and earlier also, we discussed this 2 or 3 times. Now let us see the appearance of the spectrum, how it depends. Remember, I am going to apply a radio frequency pulse and bring the magnetization here. At a immediate, instantaneously, the spin vectors, all of them are in coherence. I have to start collecting the signal immediately without any time lapse. If there is a time lapse, what happens? Some problems of phases will come into picture. So the appearance of the spectrum depends on the position of the signal at time t equal to 0. Immediately after the pulse, the time is equal to 0. You have to start collecting the signal. If pulse is applied here, you give some delay and start collecting the signal here. You get into phase problem. So you have to literally or in principle should start collecting the signal immediately after application of the pulse at time t equal to 0. If the starting point is different, we have what is called the phase errors in the sinusoidal function. Okay. Now we will incorporate this one here. This is this thing we are going to get a time domain signal. This I knew, I told you already, and we incorporated this for a decaying function. Now let us say there is a phase error that I incorporate here. This is the phase component. The phase term I am going to introduce here to the signal. So the total signal is, this is because of the phase term which is introduced and the decaying signal as a function of T2. And this is signal collected from the sample, NMR sample. Okay. So this is the total signal, including the phase error that is already present. Now, you know why the phase error comes. I will not go into this in detail because we discussed this earlier also. Now, if my signal is, detector is here, if the signal is along S-axis, I told you we have a real part which is absorptive, imaginary part which is dispersive. Both of them are exactly out of phase by 90 degrees. If both of them are exactly out of phase by 90 degrees, you collect a very real absorptive spectrum without any phase error. See, there is no phase error. The phase, the angle difference between cosine and the sine part must be exactly 90 degrees. In case if the signal is not along x-axis, it is somewhere at a different place, then what happens? There is a mixture of phases here. See, the real component is not pure absorptive and the imaginary part is not pure dispersive. You get into a mixture of phases in the spectrum. This is what happened. I saw what happens with the magnetizations along y-axis or the minus x-axis. We can even see if it is along minus x-axis, real and imaginary component gets interchanged. When your detector is along SX or x-axis, signal is along minus x-axis, you will get a real absorptive peak which is negative maximum. Okay. So this is how you should know about the phases of the signal depending upon the pulses. Okay. So let us say there is no error, but generally there will be error. So a phase error comes in all possible angles, including intermediate between absorptive and dispersive. That's what I said. At 45 degree, you have a mixture. It need not be 45 degree. It can be any angle. If they are not exactly out of phase by 90 degree, let us say there is a phase difference of 85 degree, 80 degree, 70 degree. Different angles will be there between cosine and sine. Accordingly, our signal intensity, signal, if you look at it, they have different phases. Let us say this is a perfect signal on resonance. There is no difference, there is no phase error, and cos and sine components are exactly out of phase by 90 degree. The phase error is zero. You can go on either side. I showed you the signal. It can be in the first quadrant or the third, fourth quadrant. So you can have phases both positive and negative. It can go like this. If the phase error is 45, 90 degree, 135, the phase error is exactly 180 degree, you can get a negative signal. That's what we saw. Our detector was along x-axis, magnetization was along minus x-axis. I said real and imaginary gets interchanged. Real part is a negative absorption. That's what I said. Same thing happens if you go on other side. So the phase errors can come in all possible angles. Okay? This is a very important thing. Now, how do you correct the phase? This is the phase error, and it can be frequency dependent and frequency independent. Both type of phase errors are possible. We will discuss it now. But how do you correct it? The phase correction is nothing but your real component and imaginary component. You have to adjust it, electronically, or you can do in this instrument in such a way, ensure that these two components are exactly out of phase by 90 degree. They are exactly out of phase, in which case you will get absorptive, pure absorptive spectrum like this without any phase error. So your job, what you mean by phase correction is, you are going to ensure that real and absorptive part of the signal have exact phase difference of 90 degrees. That's what is all about phase correction. We can discuss more about phase corrections and manipulation of the time domain data, how we apply window functions, everything in the next class. Right now, I'm going to stop here. Today, of course, I started telling you about the processing. I introduced you Fourier transformation. I explained to you what happens. There are many signals in the time domain, many time domain signals overlapped. What happens if you do Fourier transformation? I said you will get that many number of frequencies in the frequency domain because Fourier transformation is a linear process. And I also gave many examples of how phase errors can come and what will happen to the Fourier transformation for different types of functions. Many things we discussed today. We'll continue our discussion tomorrow on processing of the data.